we talk about multivariable calculus, there are sort of two parts to that. There's when the domain has several variables and when the range has several variables. So last time we just took a brief look at vector-valued functions of one variable, in other words, curves. So now we're going to do the opposite. We're going to look at real-valued functions of several variables, in other words, surfaces. And then we will put it all together with vector-valued functions of several variables. Before we start looking at differentiation of surfaces, we need to get familiar, get comfortable with surfaces and some techniques for visualizing them. So last time when we were looking at curves, it was easy to visualize them because we just parameterized them and then we would end up with something in the xy plane. And then we took the derivative. The derivative was easy to take because if we had component functions, like if the path equaled xt, yt, then to take the derivative of this was straightforward. Just take the derivative of each component function. So far we were able to do this just using what we know from one-dimensional calculus. So differentiation of surfaces actually also starts as an extension of one-dimensional calculus. But before we get there, we just need to take some time to examine surfaces in 3D. So we need to define these functions. Let f be a function whose domain is a subset U of Rn and whose range is contained in Rm. By this we mean that to each point x, which is x1 ... xn in U, f assigns a value f of x to an m tuple in Rm. Such functions are called Rm-valued functions, or if m equals 1, real-valued functions or scalar-valued functions. So when the values of f of x are in Rm, when it's more than one dimension, then they're called vector-valued functions. So for now, we're going to hold the range to one dimension and examine functions of several variables. So for example, if we had that f x, y, z equals x squared plus y squared plus z squared, the whole thing to the minus 3 over 2, then this function maps the set U, which is all x, y, z that do not equal 0, 0, 0 in R3 to R1. So x, y, and z in R3 is going to give us a single value in R1. And notice the exponent is negative, which means that this is actually a fraction and this is in the denominator, so this cannot be 0. The domain is everything but 0, but then the range is still going to be in a single real value for each value of x, y, and z. So we write these functions as U subset of Rn into Rm to signify that the subset U of Rn is the domain and Rm is the target. And then if we want to stress that f is multivariable, we'll either say that the function of n, that it's a function of n variables, or if n is greater than 1, a function of several variables. Okay, so for f of U with a subset of R to R, the graph of f is the subset of R2, which consists of all points x, comma, f of x in R2 for all x in U. This subset is normally thought of as a curve in R2. So what this means is that when we're just looking at regular functions that we're used to, just one-dimensional functions, when we graph them, we have from A to B, this is in x, and this is in y, and then here is f of x. So it's important to appreciate this. We spend a whole lot of time when we're learning mathematics thinking of functions as with one variable input and one variable output, right? Something like f of x equals x squared. You put in x, square it, and then you get a result. And then when we think of the graph of f of x, it's just the chart of the values of x charted onto y, right? So just for each value of x, we have a value of y, and that makes a curve. But if you take a step back and forget that this is, graphing the values of x onto y, just look at this. This is just a curve in R2. right? And the curve carved out by f of x is just, this is a subset of R2. It's a set of points in R2, and that set of points is defined by x comma f of x. So it's important to appreciate this, that we can think of the graph of a function as a subset of points in R2. So that curve in R2, the subset of x comma f of x, is called the graph of f. So to define the graph of a scalar function of several variables, we just extend this in the obvious way. The graph of a scalar function of n variables will just be a subset in n plus 1 dimensional space. Okay, so let's define that. So the graph of a function, if f of u, subset of Rn to R, is a function of n variables, then its graph consists of the set of points x1 to xn, comma, f of x1 to fn in R to the n plus 1 for x1 to xn in u. So, for example, if n equals 2, then the graph of a function f of x comma y of two variables is a surface consisting of all the points of x, y, z in space such that xy is the domain of the function and z equals f of xy. So as we already saw, if you have a function of one variable, then its graph is in R2. If we have two variables in the domain, then the graph is going to be a surface in R3. Okay, so you have two variables in the domain, and then it makes a surface, one dimension more for the graph. So this surface is the subset of R3 that is x, y, f of xy. Okay? So a graph is a defined object of a scalar function of any number of variables. Even if n equals 5, then the graph would still be a subset of R6. These surfaces exist in higher dimensions, but it's hard to picture anything bigger than 3 dimensions. So when we're learning multivariable calculus, we're going to stick with functions of 2 variables or functions of 3 variables. But remember that a function of any number of variables, the graph does exist. It's a subset of the space that's 1 dimension bigger, okay? So let's just look at a couple of examples. So if we had a function f of x comma y equals x minus y plus 2. In other words, z equals x minus y plus 2. Or in other words, x minus y minus z plus 2 equals 0. This is the equation of a plane. And the normal to this plane, you remember from our video about equations to planes, you can just read off the normal vector to this plane would be 1, minus 1, minus 1. So if we set y and z to 0, then x has to be minus 2. So it's minus 2, 0, 0 is in the plane. If we set x and z to 0, then y is 2. And if we set x and y to 0, then z is also 2. So we can sketch this. So it crosses the x-axis at negative 2. And the y-axis at 2, and the z-axis at 2. So it's crossing, these 3 points are in the plane, and the normal to the plane is 1 out and then down 1 and down 1. So the normal to the plane goes kind of down this way. So the plane is kind of sticking up this way. So maybe, see how we can do this. How about that, with these 3 points on it? Okay, and then the normal to the plane is going like down, sort of like that. Okay, not bad. So in other words, if we map all of the points that satisfy this equation, we're going to get this plane. So what we have here is that for every value of x plus y, we're going to get some value of z. And so if the xy plane is the domain, then each value of x and y will give us a value of z. So so it goes up, 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 and then down here it's going down. So it's making a surface in the xyz space. So the graph of a function with 3 variables would be a set in R4, which would look like this. And it's hard to picture that. So in that case, it helps to use what we call level sets. which are the sets obtained by setting the function equal to a constant. So we're all familiar with level sets for functions with two variables. For instance, contour maps or weather maps are all level sets of functions with two variables. For instance, with a weather map, you get these contours by setting the xy temperature function to various degrees. So here is the line where it's 10 degrees, this is the line where it's 15, and so on. And here is an elevation map of San Francisco. So the function for elevation is a two-variable function, latitude and longitude. So we set the function to different values of elevation, and we get the contours where this is Pacific Heights, here's the marina is very low, China Basin is very low, here's Twin Peaks and so on are very high, and so on. We call the level sets of functions with two variables level curves or level contours. Okay. So a level curve, let f be a function of two variables and let c be a constant. The set of all xy in the plane such that f of xy equals c is called the level curve of f with the value c. So let's look at an example to see how this works. So let's look again at what we were looking at the previous example. We had z equals x minus y plus 2. And remember, it made a plane that sort of angled down toward the negative values of x. So let's look at where this intersects z at a couple of different values. Let's look at z equals 0, and then we'll look at z equals 2 and z equals negative 2. So when z equals 0, then this is 0, and we can just move this over, and we have that y equals x plus 2. So that is a line with slope 1 that crosses the y-axis at 2. So it would cross the x-axis there. Okay, that's this line, that's z equals 0. So generally then, if we just make z any constant, then we can rewrite this to be y equals x plus minus c plus 2, right? We replaced z with c and then moved it over. Okay, so if we plug in z equals 2, then we get y equals x, and then this is 2, so minus 2, so that's it. It's just y equals x. So that is just this line. So this is z equals 2. And let's try if we do z equals minus 2, plug that into here, then we get y equals x plus 4. So it's the same slope, but it crosses the y-axis up here. This line is above the z-axis, this one is on the xy plane, and then this one is below. So if we compare that to what we had here, this is the drawing that we had before. Now here, x is here and y is here. So remember, we're rotating this around so that y is going this way. But you can see that that's what we have here. At z equals 2, we're on the z equals 2 axis, and we're above the xy plane, and the line is going kind of back and then forward in this way. You have to remember to rotate things. And then if z equals 0, both of these two lines are this line. So the plane is crossing the xy plane right here. And then if we went on down to z equals minus 2, it would be way up here at 4. And you can see it would be below the z-axis a couple, and it would go back below the xy plane. So that's how these contour lines work. The z equals 2 line is above the xy plane, and then the z equals minus 2 is below the xy plane. So the plane is sloping downward through the xy plane as you go up in y and negative in x. So for a function of 3 variables, the set obtained by making f constant is called a level surface. So let's define that. Let f be a function of 3 variables, and let c be a constant. The set of all points x, y, z in space such that f of x, y, z equals c is called a level surface of f with value c. Okay, so Just as an example, if we had f of x, y, z equals x squared plus y squared plus z squared minus 8, let's look at what would the level surface be with value 1. So if we set f x, y, z to 1, so then we would move this over and we would have 9 equals x squared. And this is just a sphere with radius 3. So what happens if we look at level surfaces with different values? As it gets bigger and smaller, the sphere grows and shrinks. So we can't really picture what the four-dimensional shape is going to look like, but somehow if we take a three-dimensional cross-section at each point, it will give us a sphere. So in some way, it grows and shrinks as the value of f of x gets bigger and smaller. So it's sort of, maybe it expands in the fourth dimension as this value gets bigger. Okay, so we can picture what a level set of three variables is because it's in three-dimensional space. And a level curve is easy because it's just on a plane. But if there's any more than three variables, then it's impossible to visualize. So we're just going to concentrate on n equals 2 and 3. Okay, so all the surfaces we've been looking at so far have been very simple. Now we're going to look at the more fun surfaces, which are called quadric surfaces. But before we do that, let's just summarize some techniques for visualizing surfaces in 3 dimensions. And then we'll look at some examples of quadric surfaces and see if we can visualize them using these techniques. So first, note any symmetries. Second, see if there's a variable missing. If so, then the surface is going to be a cylinder along the axis of the variable that's missing. And then 3, try finding level curves of different values. And then 4, try setting x to 0 or y to 0. This takes vertical slices of the surface instead of horizontal slices. This is called the method of sections. Now, this works if it's written like this, where f of xy is some function of two variables. But what we're looking at might be an implicit function, where the polynomial equals a constant. So an implicit function is something like x squared plus y squared equals 1, which makes a circle. So the way that we learned what a quote function is, where it has to pass the vertical test, a circle doesn't pass that because it has two values of y for each value of x. So this is called an implicit function because it implies a shape without really being a function in the sense that you have inputs and outputs. Because if we define this in terms of y, we would have y equals plus or minus the square root of 1 minus x squared. So this is actually two separate functions, one that goes this way and one that goes this way. So we will encounter functions of this form. If so, try to solve it. If it's easy to do, try to solve it in terms of one of the variables. If not, then just basically set y to 0, x to 0, and z to 0, and see what kinds of sections you can come up with that way. Okay, so next time we will look at the quadric surfaces using these techniques to see how the techniques work and explore the quadric surfaces. And then after that, we'll move on to differentiation. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.